populations of honeybees plummeting, scientists are looking for alternative means of pollinating crops. Conservation efforts for the real ones are underway, but in the event the problem is unfixable, researchers expect to be able to get the robotic version up and flying in about 10 years. Number 6. Flapping robot. Many insects are great flyers, but their complex movements are hard to replicate. Jellyfish, on the other hand, are simple creatures. By mimicking their movements, researchers were able to make a stable machine that can take to the air unburdened by tricky mechanics. Number 5. Bridge inspectors. Humans do what they can, but in a lot of cases, they're just too big to really get a good look in nooks, crannies, and crevices. Enter the quarter-sized machine that can access tight spots and easily travel over bolts and rivets even when it's raining. Number 4. The MAB. The Jetsons had their faithful robot Rosie, but people of the future may be turning to the cleaning skills of MAB instead. The design competition winner deploys an army of scrubbers and dusters to make a home sparkly and fresh. Number 3. MyBots. Microscopes are wonderful for inspecting things invisible to the naked eye, but they're useless when it comes to moving the matter around. That's where this little device comes in handy. Between its joystick control and small probe, it gets the tiny but tough job done. Number 2. Mini printer. Printers take up a lot of valuable desktop real estate, but there is a smaller solution, about the size of a coffee cup. This inkjet produces words and images by traveling back and forth across a piece of paper. Number 1. DNA nanobots. If genetic material is sequenced just right, it can create a microscopic structure capable of following a prescribed path and delivering a destination-specific payload. Hopes for the development are high, as someday they could be useful in seeking and destroying cancer cells without damaging healthy ones nearby. Which micro-robot do you think is the most?
So these are the different kinds of robots, which are, I would say, futuristic robots, or some robots are already being demonstrated, so that it comes on a colloquial form in due course of time. So as far as in this robot is concerned, so you might, one important aspect which I would like to explain over here is its biomimicking capability. Yes. So as far as in this biomimicking capability is concerned, so one of the key aspects about this biomimicking capability is your actuator as well as your sensor. The sensor, already we have seen that MEMS-based sensors has a capability, are flexible enough so that you can integrate with any systems. Whereas in the case of actuator is concerned, so your actuator should have a capability towards biomimicking. Okay, so because with the conventional actuators like pneumatic or with respect to hydraulic or with respect to motors, so this replicating this biomimicking capability is very difficult. In those aspects, exactly your smart material comes into the picture. Okay, so as far as smart material is concerned, so it has a wide variety of, there are different types of smart materials which are available. So basically, the interesting part with this is, so your smart material can be easily interfaced with any kind of structures. So either it might be a sensor base or it might be a control base. So your smart material should be capable enough in such a way that it can collect the signal as well as it can sense the signal as well as it can reciprocate the signal. So in those aspects, your smart material based smart actuators plays a major role. Okay. Now, as far as this slide is concerned, so this slide will give you a better clarity about the different family of smart materials which are available. So as far as if I try to look into the different families, so like one might be a shape memory alloy base, another one is a piezoelectric base, a microstructure base, an ionic base. In fact, throughout our entire presentation, so we will be going through the different types of smart material based actuators which are available and its functionality towards mechatronics and robotic systems. Okay, but even you have a wide variety of family, some selection criteria should be there to select it based for your application. So basically, so based on your application, you will be selecting these actuators for your different functionality. So one way is, so in this will give you an opening, or these are key selection criteria where you have an actuation stress and an actuation strain which is available. So as far as actuation stress is concerned, so with respect to your actuation strain, you can select your material for your actuation stress. Okay, so like in this case, for example, based on your strain requirement and based on your stress, you can select your material. In addition to that, based on the actuation characteristics also, you can select your material. In fact, these are very good examples where you can directly mimic the requirement of a microsystem using these kind of actuators. In fact, these are PDMS based. Okay, so this slide will give you an overall clarity where based on the different actuation conditions, you can select your actuator. Like actuation condition means, like for example, I have a wire, so I am just applying a certain amount of heat to it or certain amount of electrical biasing to it so that it gets displaced. So if I try to supply a heat, then it is called as thermal based actuation. If I try to supply amount of an electrical energy to it, then it is called as an electrical based actuation. When I try to have a fluid flow, it is called as fluid based actuations. And then when I try to put some kind of chemicals, then it is called as a chemical based actuation. So as far as in this electrical based actuation is concerned, so you have an electrostatic actuator, electromagnetic actuator, a magnetostructive actuator, a piezoelectric actuator, electrorheological actuator, magnetoroheological actuator, and ferrofluid actuator. In fact, electrostatic actuator means we all know. So basically, with respect to your static behavior, it moves, and with respect to your electromagnetic behavior, it displaces. So this magnetostructive and piezoelectric are belongs to the category of molecular forces. That is, based on the molecular interaction, so there is a kind of displacement which happens on the surface. For example, in the case of piezoelectric, you might have heard about it, that when a load is applied on top of it, you get an electrical biasing along the diagonals. Okay. So similarly, in the case of electrorheological or magnetoroheological system, you have a liquid. Inside the liquid, you have some metallic powders which is available. So these metallic powders are made to move back and forth, and from that back and forth, you can just harvest the system. Okay. Then we have a ferrofluidic system. So as far as in this ferrofluidic system, so you have ferromagnetic particles which are well agitated with the ferrofluidic, so that when I try to actuate the magnetic particles, so this ferrofluidic will displace, and from this ferrofluidicity, so you can expect a kind of displacement variations. Okay. Similarly, in the case of fluidic energy also, so you have a pneumatically generated force, and then you have a hydraulically generated source. So basically, based on your application, you can just select these. For example, in the case of hydraulically generated force, there are some underwater robotic systems which are available. So these underwater robotic systems uses an hydraulic liquid. It tries to pressurize it and it gives a displacement. So such kind of systems are available. Then if we try to talk about the thermal energy, any material if you take, when you try to heat it, so obviously there it is going to get displaced. But there is a material called shape memory alloy, which is, in fact, it's a quite interesting material. I work on this material. So this material has a capability to get actuated with respect to heat. So based on your heat available, you can just categorize your actuation behavior, etc. Okay, so one option would be something like this. Like for example, if I have an actuation window of something around 80 to 90, 80 to 130 degrees Celsius, and there are some kind of nickel titanium materials which are available, which can displace certain amount of displacement. In fact, I can just show you a video where they have biomimic using these shape memory alloys. Next is with respect to chemical energy. Either it might be electrostatic force, electrochemical actuator, explosive force, pyrotechnical actuators, etc. So these are available. Okay, first let us discuss about this shape memory alloy. So hope you could able to see this video. So in this video, this is a open source video where it's a kind of metal platter, metal petal of a lotus tree. Okay, so this metal is made out of shape memory. So what happens is, on the background you will be hearing the noise that there is a kind of hot air falling on it. So when a hot air gets blows, so it gets actuated. When I cut off the hot air, it comes back to its original state. So this is what is called as an actuation, where you are trying to train these actuators based on the biomimicking capability. Okay, based on this biomimicking requirement, and from that you are trying to heat the surface, and in the meantime you are trying to displace. So as far as this shape memory alloy is concerned, so if this was first discovered in 1938, so that in commercially we call it as nitinol. So basically, it is nickel titanium naval ordnance slab. So this is available in the market. Even for 500 rupees, you can get a spring. So you can just elongate the spring, and when you try to heat it, it comes back to its. In fact, I have a small video. So if I try to look into the overall perspective of this system, so it is something like when you try to look into it, how does it work? So it works on the principle of phase transformation. That is like, for example, you have a ice. So you are just heating that ice. It comes into a liquid phase. When you further heat it, it comes back to a gaseous phase. So basically, with respect to a variation in phase transformation, So you get the various characteristics coming out of it. So this is one aspect with respect to a shape memory alloy behavior. So as far as in the shape memory alloy behavior is concerned, so you have a martensite phase and you have an austenite phase in mind. So by switching between the martensite phase and the austenite phase, you get a displacement out of it. Okay, in fact, this is how it works. To give you a better clarity with the video, so this is initially on a martensite phase. Now, some person is going to deform it, which we call it as deform martensite. So he's deforming it to a level. So this is called as a deformed martensite. Now a heat is applied to it by a kind of a blower, with a blower. So approximately the heat will be in the range of, the temperature will be in the range of 80 to 130 degrees Celsius. So that is what maximum a blower gives. Now, because of the heating, it comes back to the austenite phase. So a deformed martensite, because of heating, it is on the austenite phase and then slowly comes back. In fact, this has a better response. Okay, so with respect to your amount of heat, it responds and it comes back to its shape. So as far as in this kind of shape memory alloy is concerned, so people have done our own group here using hot water. What we try to do is we try to deform it and we'll put it into an hot water so that it gets actuated and it comes back to its shape. Okay, so these are some of the aspects with respect to trading. So if you have a shape memory alloy, you can train this based on your requirement, based on the biomimicking capability, etc. So basically in those conditions, what normally it is done is some kind of fixtures are arranged. So through these fixtures, the shape memory alloy wire is being placed and it is being trained, and then it is placed in hot water to get the actuation. Okay, so in fact, this video will give you a better clarity about the different behavior of shape memory alloys. This is a kind of a one-way shape memory effect. You are trained and then you are giving a heat supply to it. So this is a kind of two-way shape memory effect. So this is a kind of composite structure where SMA is integrated inside a silicon tube. So one-way actuation is taken care by the shape memory alloy, and the return stroke is taken care by the silicon tube. So this is a thin demonstration of shape memory effect in a thin film. So this is a kind of actuation system which is being employed to get a linear displacement. So this is something kind of proper training is employed. So this is an expansion and contraction characteristics which is happening. And this is the kind of rotation characteristics. So like that, many different behaviors are there with shape memory alloy. So these behaviors are tailor-made. So based on your requirement, you can just change their behavior. Okay. So it's up to you how you are going to train. In fact, we in our laboratory, we have done some work where we have used a strain as one of the training parameter for shape memory alloy. So by straining it, we are getting a required actuation for some kind of micro robotic system. So this is one example where shape memory alloy integrated prosthetic systems are being employed, where instead of your nerve, so you have a shape memory alloy wire which is integrated into it. So when you try to give an actuation to it, your finger moves and then it gets displaced. So whatever effort you require, based on that you program your wire and you give heat to it based on the requirement. So this is on a large area where you have a 4-fingered robotic hand with SMA, so that an actuation happens and these 4-fingered moves back and forth. Okay, so this is one good example where a simulation of shape memory alloy in the form of an artificial muscle, which basically depicts biomimcs an artificial muscle demonstrated over here. So here you have a wire which is integrated and it is aligned in an appropriate fashion so that you can actuate it. So these shape memory alloys are widely used for a micro relay application also. So what people used to do is they used to fix it in the form of a tube kind of arrangement so that when you try to actuate it, it can flip. So since it's a metallic based system, one option is you can have a magnetic on one end as well as heat supply on the other end. So when I try to actuate a heat supply, this magnetic drifting happens. So based on the drifting, so you can use it as a kind of a switch which happens. Okay, so this is a kind of SMA actuator for biomedical systems. So what it's a kind of what do you call it? Your backbone. So inside this backbone, so a backbone kind of structure. So these backbones kind of structures are well connected with SMA based wires. These are trained in an appropriate fashion so that it can act as an active as well as a passive the actuator, so that it can senses and it can also appropriately move the system. Okay, so this is a kind of a SMA based robot which has a mirror capability in it. Basically, it has a prototype mirror actuation system, and you have a SMA wire which is placed over here with a wheel kind of arrangement. So by alternatively actuating it, so you can move the mirror back and forth. So when you try to move the mirror back and forth, sure, Mr. Sarang, we will address the question once this shape memory related stuff gets completed. Okay, so you can type the question in the chat. So this by actuating these wires, so basically you can move the mirror back and forth, which has its own application towards optomechatronics based systems. Basically, these are some kind of systems which we call it as intelligent mirrors. Okay, so this is one good example where the linear actuation of shape memory alloy is appropriately converted to a rotary system. Okay, so so what happens is when you try to actuate it, so you can make it in the form of a rotary robotic system so that it can be displaced in an angular rotation. In fact, this is one commercially available shape memory alloy based robot, so which shows how it balances, which confirms that these kind of smart materials has a capability towards high response. So here there are shape memory alloy wires which are being placed, and these are properly hinged, and these are some of the additive manufactured structures, and there is a camera to take a feed. And you are trying to actuate it or you are trying to balance. Okay, so this is a kind of shape memory alloy which we have demonstrated in our laboratory, which we call it as shape memory alloy bimorph. Basically, the idea of this shape memory alloy bimorph is, so one way actuation is taken care by the shape memory alloy, and the other way actuation is taken care by the polyimide on which it is coated. So it's a kind of programmable, programmed material, because as far as in this program material is concerned, what we are doing is we take a polyimide, we just strain it, and then we go for a deposition. So when we try to deposit on it, so because of its straining effect, it tries to curl it. And when I try to put it on a hot plate, it tries to make it flat. Okay. So now this is with respect to hot plate. Now, when you use a pulsed signal to it or a pulsed heating to it, appropriately you can give a higher order frequency to it. And with respect to an higher order frequency, you can use it for some kind of micro robotic applications. In fact, one micro robotic application I will show you. So we made a small honeybee kind of robot. So in this honeybee kind of robot, the flapping was taken care by the these kind of SMA based biomod. So it can go up to around 10 to 15 hertz frequency, so that when you try to actuate it, it can lift its body. So these are some of the trials which we did it in our laboratory to these such kind of SMA based biomod and how its behavior. In fact, this video will give you how frequency it was like. So this is with 5 hertz, and this entire actuator was fabricated in our lab, and it was trained in such a way that we can get it. Okay. So next we will talk about the expandable microsphere composite. Okay. So before going into it, I think there are some questions are there. We'll address the questions and we will go there. Okay. So one question is from active and passive in SMA in biomedical. Okay. See, as far as when I try to if I try to differentiate between active and passive systems. So active systems are something like you have feedback. Based on the feedback, it gets actuated. For example, I have showed you one example where there is a backbone kind of arrangement is there. So in this backbone kind of arrangement, so you have a SMA which is integrated into it. Now, based on your body dynamics, if you are giving a feed to your controller, from the controller the heat is supplied, then appropriately your backbone will move on an erector phase. So this is a closed loop system which we call it as an active based system. In the case of passive based system, so it won't be something like this. It will have its own pseudo-elastic behavior coming into it. So like in each of these shape memory alloys has a pseudo-elastic capability. That is, if you try to throw it on the wall, it won't get deformed appropriately. Okay, so it has a capability to absorb the vibration. Okay, so basically this shape memory alloy has both pseudo-elastic as well as shape memory alloy property. Certain extent, when it crosses the pseudo-elastic, automatically the shape memory alloy comes into the picture. So in those conditions, it becomes a passive type. Okay. So which material are used for shape memory alloy? Yeah, it's NITA, and there is one more material is there. It is copper combinations. So basically, we select the material based on the actuation window. That is the temperature window. In some cases, wherever we need to have where we have a window range of something around 80 to 130 degrees Celsius, there we go for this one, what you called NITA. Whereas beyond 250 to 350 degrees Celsius, then there we go for a copper-based shape memory alloy structures. So based on the window we selected, our SMAs are reprogrammable. Yes, it is reprogrammable. So I will just show you in this. If you see, this is the key slide. This is a key slide for it. So in this key slide, so you have a fixture. So based on your requirement, you are programming it. Only thing, for example, this is a virgin shape memory alloy wire. You are getting it from the market. So you are just programming it to get this desired structure. Now you say that I don't want this and I want to go for a different shape. What should I need to do is, I can change my fixture. Then I need to apply continuous cycles of heating and cooling, because if you see the mechanism behind this is an austenitic and martensitic phase shift. Okay, so what you need to do is you need to heat it to an austenite phase in the constrained condition. Then you need to immediately quench it to the martensite phase. So normally what people used to do is they used to heat it to an austenite phase rapidly and then they quench it in a liquid nitrogen. Like this, you need to do something around 60 to 80 cycles, even more than that, to get a proper accuracy. So it is reprogrammable, but after a certain life cycle, obviously it loses its shape memory property because of the oxidation behavior. Is there any passive substrate available? Yes, sir. Like for example, now active substrate means like here I have showed you that this is a kind of an active substrate, because my shape memory alloy, it is well gelled with my shape memory alloy. So whatever shape memory alloy asked to do, it does. Okay, so that is why it is called as an active type substrate. Whereas some kind of shape memory alloys are there which is directly coated on silicon wafers, okay, or sometime on glass. In those conditions, the substrate will not take part in the actual functionality. But substrate is used to get a high quality shape memory alloy so that you can peel off and you can use it for different applications. Basically, it depends upon your applications where you are using. Okay. So if there are no questions, let us go to the next type of smart actuator, which we call it as thermally actuated smart actuators. So as far as these thermally actuated smart actuators is concerned, so it is slightly away from the conventional system. To give you an understanding, I will just give you an example. You take a tissue paper, okay? So a simple tissue paper which is used for holding your coffee cup or something. So what you do is you try to roll it, you try to crumble it, and you keep a tumbler. On the tumbler, you pour a hot water. Now what you do is you just put the this crumbled tissue on top of it, so that it doesn't falls into the glass. So what happens? This hot water, from hot water, steam will come. This steam is absorbed by this tissue papers, and because of that, the tissue paper will start expanding. So when the tissue paper starts expanding, so which is something like it is getting actuated. So the reason for this is basically in this tissue paper you have lots of micro bubbles which is there. So these micro bubbles are absorbing the moisture from the water and it is getting enlarged. Okay, so this is a simple example. Similarly, you have some in a similar fashion, you have a certain amount of actuators which are there, which takes care of the flow control. For example, this is a thermoresponsive gel, which we call it as polyvinyl methyl ether. So this thermoresponsible gel is in this shape. Based on the temperature condition, it takes a different shape. Okay, so these are some kind of thermally activated gel which is available, so that it gets response to heat, and based on that your efforts are done. Okay, in fact this will give you a better clarity. This is a graph with respect to volume and the temperature. So when you try to shift your temperature, based on that your volume gets changed, and when your volume gets changed, you can use it for different applications. Okay, so this is these are some of the applications where you have a one-shot pump which is there. You have a liquid which is being placed. When you try to heat it, it tries to block the liquid flow. So by supplying a heat to it, you can just regulate your liquid flow appropriately. So these are called as unexpandable beads, and these are called as expandable beads. So based on your unexpandable and expanded beads, you can just move it. Okay, so this is your silicon wafer, and these are your beads which are available. So when you try to heat it, so these beads are capable enough in such a way that you can have a control over your displacement. So in fact, this is the larger picture of the beads which are available, so which gets activated thermally. Okay, so this is to give you a clarity where I have a flat surface. When I try to apply a kind of liquid to it, or sometime in the case if I put a thermal activator to it, so appropriately it gets displaced to a different shape. So these are the different shapes which are available, and these are the different MEMS based fabrication techniques which are available to fabricate the required structures based on the demand. Okay, so this is one good example where they have a thermally activated gels which are available. So these thermally actuated gels are creating a capillary force, and through this capillary force, it is used for some kind of microfluidic applications. Okay, and it has a bulk as well as a linear. So by actuating it, you get a bending or a bilayer. Okay. Now let us go to the next type of smart material, which has a direct relevance towards micro robotics as well as mechatronic system, which we call it as piezoelectric. So this interesting part of these piezoelectric structures are, these are piezoelectric crystals which are available. So in fact, this animation will give you a better clarity where I am just supplying a load to it. So with respect to the load, you are getting an EM. Okay, so if I try to look into the fundamental aspect of it, basically there are grains and grain boundaries which are available. So with respect to your polarized and non-polarized states, so you are trying to get your electrical actuation coming out of it. In fact, piezoelectric an extended version of it. So this is how your piezoelectric works, where you have a cantilever. The interesting part of this piezoelectric is actuators, like in this case, I am applying a load and I am getting a EMF. Vice versa, when I try to apply an EMF, appropriately it gets displaced. So the interesting part in this is, like if by giving a controlled EMF, you can have a controlled displacement coming out. In fact, you could see a controlled displacement is seen over here back and forth even on a micron scale. Okay, so the major aspect with respect to, so these are some of the characteristics with respect to piezoelectric, where in the case of piezoelectric, hysteresis plays a major role. In fact, that is one of the detrimental aspects which basically stalls piezoelectric for different applications. So for that, normally people, what they do is they used to stack the piezoelectric. So when they stack the piezoelectric appropriately, they can somehow rectify the this one. In fact, this is one good example how a piezoelectric being stacked. In fact, this is a overall construction of a piezoelectric actuators. So in this case of piezoelectric actuators, so these piezoelectric structures are stacked, and then appropriately you can have a reduction in the hysteresis. Okay, so these are some kind of piezoelectric stacks which are commercially available, which can be used for certain amount of pumping behavior. This is one piezoelectric hydraulic actuator, and this is your fluid chamber which is here, and then you have a bellow kind of arrangement. So by actuating these piezoelectric actuators, so you are just pumping the bellows, and the bellows gets displaced. Okay, so along with that, so these piezoelectric actuators has a wide variety of application towards a certain amount of mobile robots. So one robot is something like this, like you are trying, you know the mechanism of a piezoelectric. So appropriately, you are trying to have a control over the, or appropriately, you are trying to modify your leg arrangement. So in this leg arrangement, what I'm doing is, so I'm just giving a stick slip operation. So with respect to your stick slip operation, so you are just sticking to the surface and then you are slipping it so that you get a displacement out of it. So by displacing it, you get a micron level of movement coming out of it. Okay, so this is on a piezoelectric mesoscale mobile robot which is available. So in this piezoelectric mesoscale mobile robot, you have an actuation which is falling on it. So from this actuation, so you get displacement coming out of it. So in this displacement, so it moves further. Okay, so so in this for creating such kind of environment, one option would be is you have a Rubin ball which is available over here. So through this Rubin ball, an actuation is taking place. Okay, in fact, the interesting part of these kind of piezoelectric structures is, so by given a micron displacement, you can go for easy biomimicry. So this is one video which will give you a clarity. So this is a kind of a piezoelectric arrangement which is available, and this is a snail. So it is competing with snail. Okay, so almost it's a kind of biomimicking capability which is being generated at this layer. And there is a stick slip arrangement, which is something called, we call it as a plowing type arrangement, which is there. So this plowing type arrangement is it is giving an effort in this direction, and it tries to pull it in this stroke so that it is matching with the speed of a snail. Okay, and an expansion of this, you have a wide variety of robotic systems, mobile robotic systems which are available. So these mobile robotic systems have certain amount of Ruby kind of foot which is available, and these Ruby foots are used for movement of such kind of manipulation unit. In fact, for testing some kind of electronic circuits, such kind of manipulation units have its own applications. Okay, so this is one of the interesting macro level based mobile system. Okay, where you have a piezoelectric actuator which is being placed over here. These piezoelectric actuators will try to vibrate at a high frequency. So when it vibrates as a high frequency, from this it is being transferred to the frame body, and from the frame body there is a movement which happens on the surface. So what happens is when this frame body moves, so you get based on the vibration it moves, and you can just manipulate your moving direction based on the vibration. If this vibration is in this particular frequency, you get a forward stroke. If it is on the reverse vibration, so then it can move on a backward stroke. Okay, so so this is some kind of what I call a macro level systems which are available. Okay, so it has its own nitty-gritties. Next one, what we are going to talk about is called as a ferrofluid based micro robotic system. So as far as in this ferrofluid based micro robotic system is concerned, so what we are trying to do is, I think better first we will see how does it works. 1 minute.
Hello, sir. Your voice is not coming.
No, 1 minute. I am just getting that video. 1 minute.
Okay, sir. Okay, okay.
I think I missed that video. Anyway, I'll just show it to you later. So this ferrofluidic is something like, okay, so this is electroactive polymer. Okay, in this ferrofluidic, so you have nanoparticles which is being fixed to a certain amount of layers or a certain amount of ferrofluidic layers, so that you can just actuate it based on your requirement. It is almost similar to your magnetorheological based system. So in this system, so what happens is, so by giving an electrical biasing or an external biasing, you can appropriately change the property of it. In fact, in this case, what normally people used to do is, so people used to keep such kind of ferrofluidic layer on these ferrofluidic cushioning on this, and by giving an electrical biasing or kind of magnetic biasing to it, so it acts as a damping medium towards the direction of the motion. Okay. So the next one which I would like to discuss to you is about a magnetostructive material. So this is a magnetostructive material which is available, where you could see a thin foil. So by applying an external magnetic field, you can control the over. So by giving an actuation to it, you can see it is getting displaced. So almost in the case of magnetostructive also, it is almost similar to piezoelectric structures. So here the domain plays a major role. In the case of piezoelectric, we were applying an electrical biasing. In the case of magnetostructive, so we will be applying certain amount of magnetic field. So by applying a magnetic field, so the domains gets aligned, and with respect to that, you get a displacement coming out of it. So the interesting part of this is, this will give you a better comparison with respect to piezoelectric. Teflon D is an example of magnetostructive system. And SMA is the one where it works based on the thermal actuation. So if I try to look into the energy density, so basically this has a better energy density compared to the other systems. Whereas if I try to look into the overall cost aspect point of view, this is pretty heavy. Where as far as elongation point of view, shape memory alloy has a better elongation compared to the PZT and terphenol. So basically for a higher order elongation, normally people used to prefer shape memory alloy. So this is one good example where you could see there is a kind of floating object which is there, which is being actuated with a magnetic field. So by giving a biasing to it, so you can make the system to move. See, the system is getting displaced. So this is one good information about a magnetostructive system. So these magnetostructive systems are widely used for some kind of micropumps kind of arrangement. So in this micropump kind of arrangement, you have a thin film which is available. So this, using this thin film, you can actuate it and you can use for pumping, or sometimes it is used for valve closing or valve open. So this is one arrangement where you have a valve closing or a valve opening system. So by actuating it, you can have a control over the flow rate. So this is one microstructure system which they have developed a small micro robotic fish out of it. So this is how it shows. So you're trying to give a mechanism to it by applying an appropriate magnetic field. Okay. Now let us go to the next kind of smart material based actuator, which we call it as electroactive polymer based actuator. So this is an example of an electroactive polymer based actuator. So in this you have a polymer which is being actuated. So by actuating it, it is displaced. So the interesting part in this is you can program your displacement based with respect to time. So that is what it is being experimented over here. So that you can program your displacement with respect to time. Okay, so the advantage of going such kind of electroactive polymer, so this acts similar to your artificial muscle. Okay, so but actuation is done either through electrical or sometimes it is even through light also. So in those electroactive polymers, so what people used to do is people used to fill it with some kind of elastic medium so that these elastic medium gets actuated, and based on your actuation, there will be a displacement which is being present over here. Okay, so in fact, this is one good example where how your electroactive polymer works for some kind of fluid platform based applications. Okay, so this as far as this electroactive polymer is concerned, so this electroactive polymer has a very big family. So in this family, you have a silicon elastomer, you have a polymer, you have a shape memory alloy which is available. Basically, by changing your actuation behavior, you can employ the different, you can actuate the different electroactive capability. So by actuating the different electroactive capability, it gets displaced, and then it gives you a wider perspective about the different actuation conditions. Basically, in a nutshell, it is something like this. Like based on your application, you can select your electroactive polymer. So in fact, the fabrication requires some amount of understanding about chemistry, about polymer matrix, etc. But still, it has its own advantage. By tuning it, you can use it for different soft robotic applications. So in fact, this will give you a better clarity how good or how good is its response. Okay. So the next one, what we are going to talk about is called as ionic electroactive polymer. So in this ionic electroactive polymer, what normally people used to do is people used to have a Teflon tubes. So inside these Teflon tubes, there are some amount of fluid which is being filled, and there are some kind of hydrogel fibers which are available. So when you try to actuate it, so these hydrogel fibers will try to move back and forth. So when it moves back and forth, so it will give a certain amount of elongation to the system. So in fact, this is one example where how a soft adaptive gripper is used. So it has a capability to get a different what do you call it, actuation as well as a different gripping mechanisms. Okay, so these electronic polymers are basically, it has a capability for bending. In fact, in this also you can go for a composite layer so that you can make some kind of bimorph structures to improve its response time as well as to improve its capability in handling any kind of components or systems. So that is one major advantage of using these kind of ionic polymers. In fact, this is one good example where it's a kind of insert kind of arrangement which shows a micromechanism capability using these electroactive polymers. You could see there is a micro motion which is being integrated. So with respect to this micro motion, you can biomimic an insect kind of arrangement. Okay, this is quite an interesting material which we call it as oxatic material. So normally when there is a sponge there, and when you try to pull it, so there will be a kind of
Are we testing the next?
it will result in a reduction along the diamond. Okay, so this is what we call it as a Poisson ratio, okay, which you call it as a positive Poisson ratio. Whereas in this kind of oxidic form, it behaves completely different. That is, when you try to pull it, there will be a kind of elongation along your width. So this concept is called as negative Poisson ratio. So this oxidative form is completely a new material which is being evolving for which has quite a good amount of application towards smart actuators. For one good example, like there is a block which is there in your heart. So to remove the block, so such kind of actuators can be used so that it can be fed into your wall, and then you try to pull it along both the sides, so that what happens is, because of the negative Poisson ratio, there will be an increase in the breadth, so that when you try to pull it off, you can easily remove the blocks, or you can easily remove the scale. This is one interesting aspect with these kind of oxidic forms. In fact, this is on a preliminary level study which we have done it in our lab. So in fact, on a wider spectrum also, people are attempting such kind of oxidic behaviors. So oxidic behavior means the structure will be on an oxidic phase. So it has a hexagonal structure or a pentagonal structure or a octagonal structure, so that wherever you pull it, there will be a kind of expansion coming out of it. So basically the idea is, this is your conventional form and this is your oxidic form. So you need to transform your structure from a conventional to an oxidic to get that such kind of behavior. Okay, so this is your normal form and this is your oxidic form. So you are trying to heat it to get such kind of behavior out of. And these are some kind of stress analysis which we did it in our lab, and we did some negative Poisson ratio calculations. In fact, this is one important application. So what we are basically looking for. Okay. So where you can just remove these block walls. Second most important thing is, as far as in this oxidic material is concerned, so the interesting part in this is, it has a capability to absorb vibration. So what you can do is, you can directly employ in some kind of what you call weapons or in kind of gun stills, so that wherever there is quite a good amount of vibration is there, this can be easily observed. The last part what we are going to talk about is called as a smart hydrogel. So as far as in this smart hydrogel is concerned, so it's a kind of a gel kind of structure. So inside these gel kind of structures, so you have a liquid which is available. So you try to pressurize this liquid. So when you try to pressurize this liquid, so what happens is, there will be an elongation in your structure. So with respect to your elongation, so you get a displacement. In fact, I would like to show you one reference about this hydrogel. So this is your hydrogel actuator, which tries to displace a ball in an underwater condition. So this is a hydrogel which is trying to catch a fish. So inside these hydrogel layers, so there is a pressurized fluid which is being placed, and it gets activated. So these are some kind of hydrogel structures which are of recent demand. In fact, these are some kind of smart actuators which has a capability towards direct biomimicry, even from micro level to a macro level. And people are working on it for different other applications, such as microsurgery, some kind of scaffolding, etc. And sometimes it is used as a smart clusters. Okay, so this is a kind of magnetic hydrogel. So by actuating it, you can get a displacement. So interesting part in this is, you can hold it for a particular time. Okay, so these magnetic hydrogels are can be used for some kind of self-assemblies robot. And in fact, in the first slide, I have shown you the different types of robots. In that one self-assembly robot which was available can be easily mechanized using these kind of systems. Okay, and it has its own application for different biomedical related aspects as well. Okay, so with this, we would like to close the lecture on smart actuators. I would be happy to address any kind of questions. Then we will move to optomechatronic systems.
Sir, some questions are there
So
in the
what
chat
is
box,
the
sir.
What is the difference between wafer and substrate in MEMS? Which one is thicker? Okay. See, substrate is a terminology which is used for deposition or coating. Okay, deposition. I should say, like for example, I can just show you one. Okay, this is your substrate. Over the substrate, you can grow nanostructures. This is the substrate, or you can go thin films. So these are some examples where you can do some certain amount of deposition on it. So this substrate will act as a what I would say uh, a supporting structure so that your deposition can happen on it. So your deposition will start getting the characteristics of the substrate. Okay, for example, in many electronics applications, people used to go for small thin films. Okay, so in the case of thin films, so people used to deposit on a silicon wafer. So the reason for depositing it on a silicon wafer is so the whatever capability the silicon wafer has, that can be easily transferred to the film what you read. Okay, so that is the major advantage of going for such kind of substrate. Whereas wafer is something like it's a kind of support what I would say a removing layer, okay, over which you try to build it. One book, some book references. Actually, there is a group on IISc Bangalore, so they work on micro robotics and they work on MEMS-based systems. Okay, in fact, Professor Anand Sures's book is a very good reference for learning such kind of micromechanics. How to learn smart actuators. See, smart actuator is something kind of an interesting new area, I should say. So we got fascinated because of some kind of applications, and we also understand that these kind of smart actuators were not focused on an Indian context when we started our research. So that's how we started focusing on the smart actuators. So our group is also planning to come up with some book on smart actuators. Probably I can just share it to you later. What is the major difference between NEMS and MEMS? Okay, so as the name suggests that it is basically on a micro and a nano scale. Okay, whereas in the case of boundary is concerned, so obviously based on your application, your MEMS has a different scaling loss. Your NEMS has a different scaling loss. Your NEMS scaling loss is completely, it's a different ballgame because there you have a nanomaterial environment. So when you try to work on the nanomaterial environment, you have a fluidic place is there. So based on your nanofluidic place, you will be having a kind of displacement coming into the picture. Okay, so basically it depends upon your scaling. Okay, so if there are no questions, shall we go to the next topic on optical optomechatronics? Okay. Dr. Vasu,
Yeah,
can we
yeah,
have a short break
some
for
breaks.
5 minutes and
We'll
we
have
start?
yeah, we will have some 10 minutes break, sir. Okay.
Okay, okay. So 3:50. What time we can start back? 3:10 or 3:15?
3:15. 3:15.
3:15. Okay, okay, okay.
Okay.
Sure.